This is our 30-second teaser. What if we could remove, as if by magic, all the difficulty and complexity of differential calculus from the physics curriculum? In one fell swoop, poof, it's gone. Guess what? We can. I'll make the case in this video. The graphs on this page represent the results of analyses of physical systems in each of the major branches of classical physics. They were obtained using computational calculus, which is little more than simple arithmetic, and they are, with one exception, unobtainable using analytic calculus. In this video, we will describe the analysis leading to the first graph, the Apollo trajectory, in some detail. The other analyses will be summarized at the end of the video. In order to see what needs to be done, it's necessary to see what is being done. So we'll spend some time on context. In 1989, a paper was published by two well-known physicists, Jack Wilson and E.F. Reddish, titled Using Computers in Teaching Physics, and subtitled Computers Can Revolutionize Not Only the Way We Teach Physics, but also what physics we teach. Jack Wilson was the executive officer of the American Association of Physics Teachers, the AAPT, when the paper was published, and he held that position for 10 years. The paper includes the following. The computer has revolutionized the way we do physics, but surprisingly, it has not significantly altered the way we teach physics. Talks and papers on teaching with computers fill the meetings and journals of the American Association of Physics Teachers, and workshops on the topic abound. Yet the real impact of computers in the classroom is slight. And we have made a virtue of necessity by selecting a palette of topics that are mathematically accessible to students, and then defining those topics as the ones necessary to the students' conceptual development. A lot has changed since 1989. Today, we see that physics education research, acronym PER, is now regarded as a field of study in its own right, and there are many academics who specialize in it. There is also an organization of physics teachers, Partnership for the Integration of Computation into Undergraduate Physics, acronym PICUP, dedicated to increasing the use of computers in physics education. And after spending many millions of dollars trying unsuccessfully to improve math education 20 years ago, the National Science Foundation is now spending millions trying to improve STEM education. An example, an NSF grant of $1,120,807 for a study titled Research on the Development of an Assessment to Measure Kindergarten Children's Abilities to Reason Computationally with Mathematical Problem-Solving Skills. So, we see that a lot of attention and a lot of money has been directed to improving technical education with computers. And yet, the core courses in the physics curriculum haven't changed appreciably since the first paper was written in 1989. A retrospective article published in The Physics Teacher in 2016, titled 100 Years of Attempts to Transform Physics Education, doesn't mention computers or computation. The previous editor of the American Journal of Physics summed it up in a satirical article written in 2017, quoting, "Attempts to improve physics instruction suggest that there is a fundamental barrier to the human learning of physics." And, more to the point, we start with the observation that the failure to improve instruction is, in itself, a very important insight. In an era with spectacular progress in a wide variety of fields, the efforts of physicists have proved to be wanting in only two areas: quantum gravity and teaching. So, 30 years ago, the promise of computers was recognized, and the problems with the then current curriculum identified. And since that time, a lot of work has been done by many academics, and a lot of money has been spent by the government. And yet, nothing has happened. What gives? Let's get to the bottom of this. Our first goal is to identify precisely how computers have changed physics. Everything else will follow from that. Classical physics makes up the bulk of the university physics program for the first 2 years. Classical physics is the mathematical analysis of physical systems and processes. Since Newton, the basic paradigm for the analysis of a physical system has been, first, state the laws of physics governing the system. Laws of physics governing how things change are written as differential equations. Second, derive a differential equation model of the system from the physical laws governing it. And third, analyze the differential equation model with the goal of predicting the performance of the system. To predict system performance, the model equations must be solved. Once stated, the paradigm is key to everything. But the above paradigm is never stated in the classroom or in physics texts because it makes the problem obvious. The problem is differential equations. Differential equations are an advanced topic in calculus. They are difficult to solve, and what's worse, most are impossible to solve. So, it is no wonder that physics education is so difficult. Physics itself is very difficult because the differential equation models for most systems do not have analytic solutions. Most real systems cannot be analyzed with analytic calculus. However, there is good news. The computer makes it trivially easy to compute solutions to differential equations, even the analytically unsolvable ones. Moreover, you don't need to know any analytic calculus to compute solutions to differential equations using the computer. Computers do not solve differential equations by speeding up the methods used in analytic calculus. Instead, they compute solutions in an entirely different way that bypasses analytic calculus altogether. Computers have revolutionized physics and engineering outside the classroom because they can be used to analyze differential equation models of physical systems that cannot be analyzed using traditional analytic calculus. What systems can't be analyzed using analytic calculus? Just about all of them. Computational methods also have a huge pedagogical advantage. They are trivially easy and intuitively transparent. The basic method can be taught to a high school science student with no previous exposure to calculus in a single 1-hour lecture. Another plus in teaching computational methods is that computational methods are the norm in analyzing physical systems outside the classroom. To compare the analytic and computational approaches to teaching physics, we will choose a representative subject in classical physics, central force motion. First, we'll review how central force motion is currently taught in high school, in lower division university physics courses, and in upper division physics courses. Then we'll show how it will be taught in a new curriculum that incorporates computational methods. Central force motion as taught in high school physics. We will analyze the trajectory of an apple falling from a tree, and we will use the paradigm given earlier. The paradigm is used in high school, although differential equations are not identified as such. First, the physical laws. The physical laws governing central force motion are taught in high school physics classes. They are Newton's law of gravity. The force of gravity equals the gravitational constant times the product of the masses divided by the distance between the masses squared. And Newton's second law of motion, force equals mass times acceleration. Step 1 of the paradigm is complete in the first high school physics class. The mathematical model for central force motion is derived by substituting the formula for the force of gravity into the second law of motion and dividing by the mass of the object to obtain acceleration equals minus g times the mass of the earth divided by r squared. Step 2 of the paradigm is complete in the first high school physics class. In high school, things go south when we get to step number 3. We would like to solve the equation derived in step 2 and use the solution to analyze the performance of representative systems, falling objects, orbits, rocket trajectories, etc. However, the high school student hasn't studied the analytic calculus necessary to solve this equation. So, in the high school class, a simpler model is given. The simple model assumes that the force of gravity is constant, and it is a good model for trajectories near the surface of the Earth, but useless for orbits or rocket trajectories. With gravity constant, the model equation becomes acceleration equals minus 9.8 meters per second squared, and the problem is restricted to determining 1D trajectories of falling objects near the surface of the Earth, without considering drag due to air. Let's examine in detail how the high school class proceeds to solve the restricted problem. When the object, let's say an apple, begins to fall at time t equals 0, the apple's velocity is 0. Since it accelerates at a constant value of minus 9.8 meters per second squared, the velocity of the apple at time t is minus 9.8 times t. A simple heuristic argument is used to show that when the velocity of the apple is given by v of t equals minus 9.8 times t, then the distance traveled by the apple at time t is given by d of t equals minus 9.8 divided by 2 times t squared. This is the same solution that would be obtained using Newton's analytic calculus to solve the simple differential equation model. But the heuristic argument doesn't require any knowledge of calculus. Now the student can compute and thus predict the trajectories of falling apples and also objects thrown near the surface of the Earth, as the horizontal and vertical velocities are independent and the horizontal velocity is constant. Central force motion as taught in the university, lower division. The first 2 years of a typical university physics curriculum are centered on classical physics in the form of mechanics and electrodynamics. Central force motion is covered as a part of mechanics. For our purposes, we will review the coverage of central force motion given in the popular and representative text, University Physics by Young and Friedman, that is used in the introductory physics course at the University of South Florida. This is the index to the book. The chapter on gravitation starts on page 402 and covers various aspects of the subject. We'll focus on the analysis of planetary motion. In the section, The Motion of Satellites, Newton's law of gravity and the second law of motion are used to derive the velocity of a satellite in a circular orbit of radius r. In the following section, Kepler's laws are stated. Kepler developed his laws from observations, and they are not derived in the text. The text notes, Newton was able to show that for a body acted on by an attractive force proportional to 1 over r squared, the only possible closed orbits are a circle or an ellipse. He also showed that open orbits must be parabolas or hyperbolas. These results can be derived by a straightforward application of Newton's laws and the law of gravitation, together with a lot more differential equations than we're ready for. It is possible to use Kepler's laws to derive Kepler's equation, and by solving this equation, compute a planet's position as a function of time, as we will see later, but that is not covered in the text. Central force motion is also covered in an upper division course at the University of South Florida in classical dynamics. The course uses the popular and representative text, Classical Dynamics by Thornton and Marion. This is the index to the book. The chapter on central force motion starts on page 287 and covers various aspects of generalized central force motion. We'll focus on the analysis of planetary motion. The section Planetary Motion, Kepler's Problem, includes a derivation of a generalization of Kepler's laws from Newton's law of gravity and the second law of motion. Kepler's first law is that the planets follow elliptical orbits, and it can be used to plot orbits as a function of angle theta, as is shown in the book. However, predicting a planet's trajectory requires knowing the planet's position in the orbit as a function of time. This is known as Kepler's problem. Quoting, "The problem is to find the position or speed of the two bodies over time." Despite the title of the section, the book does not address Kepler's problem. Planetary motion is an example of the two-body problem. Rocket trajectories from one celestial body to another are examples of the three-body problem, which is completely intractable analytically, but straightforward computationally. The book has a section on rocket motion, which I'll quote. The actual motion of a rocket attempting to leave Earth's gravitational field is quite complicated. For analytical purposes, we begin by making several assumptions. The rocket will have only vertical motion with no horizontal component. We neglect air resistance and assume that the acceleration of gravity is constant with height. We also assume that the burn rate of the fuel is constant. All these factors that are neglected can reasonably be included with a numerical analysis by computer. So, we're back to the high school model of constant gravity, along with even more restrictions to make the problem solvable using analytic methods, but with one factor included, the changing weight of the rocket as fuel is consumed, so that the problem requires 2 pages of calculus to solve. A perfect example of tailoring the problem to the mathematics available. So, we've studied central force motion on 3 occasions and graduated with a degree in physics, but we still can't calculate an orbit. Well, how did Kepler and Newton manage to do it? In historical context, calculating an orbit is equivalent to solving Kepler's equation, which we haven't seen yet, as it isn't covered in Thornton's book. It is m equals E minus epsilon sine E, where m is the planet's mean anomaly, epsilon the orbit eccentricity, and E the planet's eccentric anomaly. The time into orbit can be calculated from the mean anomaly, and the planet's position can be calculated from the eccentric anomaly. So all that is needed to compute position as a function of time is to invert Kepler's equation to get E as a function of m. However, Kepler's equation is transcendental, and hence inverting it is not easy. Both Kepler and Newton developed numerical methods to invert the equation. Newton's method for finding roots to an equation is still state-of-the-art. J.L. Lagrange, a French mathematician, published the first analytic solution in 1771 in the form of an infinite series, as shown. We've studied central force motion in 3 courses, in high school, in the University Lower Division, and in the Upper Division. And we still can't compute an orbit, much less a rocket trajectory. And in fact, the idea of actually solving the problem, that is, computing an orbit or a rocket trajectory, has never been mentioned. So again, this is indicative of the criticism appearing in the Using Computers in Teaching Physics article. The courses in the current curriculum are designed around the limitations of analytic calculus. Now let's see how the subject of central force motion would be treated in a curriculum based on computational calculus. The course will be based on modeling physical systems with differential equations and analyzing those models with computational calculus. Wait a minute. Differential equations in high school? From Using Computers in Teaching Physics, we read, differential equations are rarely introduced until the first advanced courses after the introductory sequence, and partial differential equations appear in some junior and many senior courses. It was true then, and it's true now. A physics major at USF takes their first and only course in differential equations in the junior year. So this represents a real and radical change to the physics curriculum. How is it even possible? What is a differential equation? In the context of analyzing motion, a differential equation is an equation for velocity or acceleration. The standard calculus notation for the function representing the rate of change or velocity of a variable f is f prime. For us, this is just a naming convention, nothing more. The function representing the acceleration of f is named f double prime. So if the system to be analyzed is a falling apple and its position is represented by the function p of t, the function representing its velocity will be named p prime of t, and the function representing its acceleration will be named p double prime of t. Here is the key distinction that makes the early introduction of differential equations possible. Differential equations are used in physics in two ways. They are used descriptively to state physical laws and to model physical systems. Used descriptively, there is nothing difficult about differential equations. They are just algebraic equations for velocity or acceleration. Only when you try to analytically solve differential equations do they become difficult. We won't do that. We will use differential equations descriptively and compute solutions to them using computational calculus. Here is a little secret that they don't tell you in school, secondary, or university. The purpose of calculus is to solve differential equations. That is, given a function for velocity or rate of change, to determine distance or total change. And it's very easy to do if you have a computer. Given a rate equation, p prime of t equals some function q of t, Euler's method translates it to a computational equation by rote. The computational equation corresponding to p prime of t equals q of t is p of t plus delta t equals p of t plus p prime of t times delta t, which equals p of t plus q of t times delta t, and uses that equation to compute the solution directly. It's as simple as that. Euler's method works by dividing the time interval of interest, 0 to t, into n short subintervals of length delta t, with endpoints t1, t2, t3, tn plus 1, and using the computational equation to compute the total change in p step by step. We'll demonstrate by computing 5 seconds of the trajectory of a falling apple whose velocity is given by the simple gravity model as p prime of t equals minus 10 times t. Since we're doing this by hand, we will use just 2 subintervals, each of 2.5 seconds in length. The velocity at the start of the first subinterval, v of 0, is 0. So Euler's method computes the solution for the first subinterval as falling with velocity 0. Since the velocity is 0, the apple doesn't fall at all, and its position at the end of the subinterval is still 100, as shown by the graph on the left, with the computed solution shown in red. The velocity at the start of the second subinterval is minus 10 times 2.5 equals minus 25. So Euler's method computes the solution for the second subinterval as falling with velocity minus 25. It falls for 2.5 seconds with a velocity of minus 25 for a total of minus 62.5. So its position at the end of the subinterval is 100 minus 62.5 was 37.5. The calculations are shown on the next slide, and, well, this is a lousy approximation, but take heart. Things improve as the subinterval size is reduced. The graph on the right shows the true velocity in blue and the velocity of the computed solution in red. This slide shows the computations for the trajectory shown in red. In addition, the graphs show computed solutions when delta t equals 1 second and when delta t equals 0.1 second, along with the true solution. Euler's method requires lots of computations to obtain an accurate result and was not practical before the advent of computers. However, with the advent of computers, computational methods based on Euler's method have become the dominant method of analyzing physical systems in physics and engineering outside the classroom. Programming Euler's method is straightforward, and the programming details for the examples in the video are given in a paper linked in the description to this video, and another link is provided to the MATLAB programs. Suffice it to say that the programming is almost by rote. Each program has the same structure. An initialization section where constants and model and program parameters are initialized, a for loop which steps through the subintervals executing the computational equations, and a graphing section for presenting the results. Modern languages like MATLAB and Python have built-in graphing functions which produce the graphs directly from the data. We will use Euler's method for computing solutions to differential equation models of physical systems. A differential equation model of a physical system consists of a set of variables, v1, v2, vn, that define the state of the system. These variables are called state variables, and a first-order differential or rate equation for each state variable of the form vi prime of t equals fi, function of the state variables at time t. So that when you're given the values of the state variables at time t, you're able to calculate the rate of change of each of the state variables. So we're now ready for our first non-trivial example. Newton's model for a falling object in one dimension consists of state variables for position, r, the distance between the object and the center of the earth, and velocity, v. And the rate equations r prime of t equals v of t, and v prime of t equals minus g times the mass of the earth divided by r of t squared. Euler's method translates each rate equation to a computational equation. R at time ti plus 1 equals r at time ti plus v of ti times delta t, and v of ti plus 1 equals v of ti plus minus g times the mass of the earth divided by r of ti squared, all times delta t. This slide shows the hand computation of 5 seconds of the trajectory of an apple falling from a height of 100 meters. The initial values of the state variables are given. R at time 0 is 100 meters, plus the radius of the earth, and v at time 0 is 0. Take a moment to look this slide over and make sure you are fully comfortable with the computations before proceeding. Next, orbits. The state variables for a falling or orbiting object in 2 dimensions are its position coordinates, x and y, and its x and y velocities, which we'll denote by vx and vy. With the Earth at location 0, 0, the distance from the Earth to the satellite is given by r, where r equals the square root of x squared plus y squared. And the magnitude of the gravitational acceleration on the satellite is minus g times the mass of the Earth divided by r squared. The coordinates of a unit vector pointing from the Earth to the satellite are x over r and y over r. Thus, the x component of the satellite's acceleration is a times x over r, and the y component is a times y over r. And now we can write the rate equations for the state variables as shown. The computational equations corresponding to the rate equations are written pretty much by rote. And now we're ready to compute orbits, comet trajectories, etc. A trajectory is determined entirely by the initial conditions of the satellite, that is, its initial position and velocity. The first graph shows the space station orbit. The program graphs the trajectory and then adds an outline of the Earth to the graph for reference. The second graph shows an elliptical orbit, and the third a hyperbolic trajectory of a comet. Orbits are examples of the two-body problem. If we had a rocket, say a rocket that travels from the Earth to the Moon, we have a three-body problem. While the two-body problem is very difficult analytically, the three-body problem is completely intractable. The rocket is pulled by Earth's gravity and the Moon's gravity, so there are two forces that are accelerating the rocket. There are state variables for the moon's position and velocity and for the rocket's position and velocity, for a total of 8 state variables. The moon is modeled as a satellite, as we've already done. We can calculate the vector from the moon to the rocket, the distance from the moon to the rocket, the magnitude of the acceleration due to the moon's gravity, and the x and y components of that acceleration, as shown. The rate of change of the rocket's velocity variables have 2 terms, the first due to the acceleration due to Earth's gravity, and the second due to the acceleration due to the moon's gravity. The computational equations follow directly from the rate equations. We want to shoot a rocket straight up from the surface of the Earth so that it hits the moon. First, we determine by trial and error what initial velocity for the rocket will take it just up to the altitude of the moon's orbit. Then, we set the initial position of the moon so that it reaches the point just above the rocket's launch site at the time that the rocket reaches the moon's altitude. Not elegant, but it's effective. The result, a hit. The program adds the moon's outline when the rocket hits it, for reference. We can model a guidance thruster on the rocket with a guidance acceleration vector, g sub x and g sub y, that is pre-programmed or calculated on the fly. Then, by positioning the moon so that the rocket just misses, and applying an appropriate guidance nudge as the rocket passes by the moon, we can put the rocket into orbit around the moon, giving us the Apollo trajectory. The computational equations are modified by adding the velocity changes due to the guidance acceleration directly as shown. Then we determine gx and gy by trial and error. An acceleration in the minus y direction, effectively slowing the rocket down just as it passes by the moon, does the trick. Suppose we don't apply the guidance nudge and let the rocket fly by the moon. The result is something known as a slingshot or gravity assist trajectory. The trajectory is shown on the left. The graph on the right shows the total and the x and y velocities as the rocket passes the moon. Note that the top line in the graph, the rocket's total velocity, is much greater after the rocket passes the moon than before. This is known as the slingshot effect, and it plays an essential role in rocket missions to the outer planets. On August 5, 2011, the United States launched the Juno probe to Jupiter. The probe was launched from a low Earth orbit into a 2-year orbit around the Sun. In October of 2013, the probe returned to Earth, and the slingshot effect propelled the probe toward Jupiter. It arrived at Jupiter in July 2016. The figure on the left is a NASA graphic showing the Juno trajectory. The figure on the right is our version of the trajectory, showing the Earth's trajectory in blue and the rocket's trajectory in red. Both MATLAB and Python have 3D plotting functions. One of the amazing things about this trajectory is that it is completely unguided until it reaches Jupiter, except for one guidance boost applied about 1 year into the flight, as indicated on the NASA graphic and on the simulation. We've examined in some detail how central force motion is taught in the current physics curriculum and in a new curriculum based on the analysis of differential equation models of physical systems using computational calculus. And we've seen the extraordinary difference in the results obtained. A college physics graduate who has only studied analytic methods cannot compute an elliptical orbit, while a high school student who has studied computational methods can analyze complex rocket trajectories like the Apollo mission. And note that the engineers at NASA don't use analytic calculus to analyze rocket trajectories. They use computational calculus. The most powerful tool for analyzing physical systems is missing in the educational system. Incorporating differential equations and computational calculus into all the courses in classical physics will transform physics education. What about the downside? What is lost? Nothing will be lost in the new curriculum because the student will take the same courses in analytic calculus as in the old curriculum, and analytic calculus will be used when appropriate. There is still one more advantage to using the computer. Quoting using computers and teaching physics one more time, the step-by-step in time approach is also a much more concrete, even transparent approach to this problem. We could repeat the comparative analysis of analytic versus computational calculus for analyzing systems in all branches of classical physics, and the results would be the same. The tables below summarize the analyses of systems in 8 branches of classical physics, and in every case but one, the RLC circuit, the systems are intractable using analytic calculus. As the systems become more complicated, the differential equation models become more complicated, and the analyses become more complicated, especially when switching from ordinary to partial differential equations. However, the level of difficulty remains close to being the same. The difference in complexity in analyzing the more complicated versus the simpler systems is similar to the difference in difficulty in assembling a jigsaw puzzle with 100 pieces versus assembling one with 25 pieces. The basic operations are the same. The more complicated systems just require more of them. The first table shows the analyses of systems governed by laws of physics written as ordinary differential equations. For each analysis, the table contains the physical laws governing the system, the differential equation model of the system, the computational equations for the model, and the results of the analysis shown as a graph. The systems are the moon orbit, the impulse response of an RLC circuit, and a rigid body rocket launched into orbit. All the systems in this table and the two that follow are intractable analytically with one exception. That is the RLC impulse response, which can be obtained analytically using the Laplace transform. However, if a nonlinear element were added to the circuit, it too would become intractable analytically. The finite difference method is an extension of Euler's method for handling partial differential equations, and it translates partial differential equations to computational equations by rote and is one-to-one. Because there are more variables, more dimensions, and second-order differential equations, the length of the formulas can be intimidating, but their derivation for the most part is straightforward. The first row shows the analysis of heat transfer in a 2D plate with a heat source in the interior and fixed and floating boundary conditions. The second row shows the analysis of a square drum. The finite difference method is easier for square domains. The initial wave originated at the center, and it is shown being reflected from the fixed boundaries. Any of these analyses can be run as a simulation by graphing the results in each iteration of the program for loop and pausing for a fraction of a second so the graph can be seen. The third row shows the analysis of stress and strain in an elastic plate with a cutout in the center and a downward traction applied along the top. The first row shows the analysis of fluid flow over a backward step. This analysis is complicated by the fact that the differential equation model does not have a rate equation for one of the state variables, fluid pressure. So in this one instance, the cookbook fails us, and an ad hoc method has to be derived for computing pressure. The second row shows the analysis of an electromagnetic wave generated along the left border and traveling to the right and hitting a barrier with a wide slit in the center. Maxwell's equations in differential form are the model for electromagnetic radiation, and the finite difference method, right out of the box, translates them to computational equations.